Hey guys, this is Darshan Lokhande. I am a pre-final year BTech CSE student at IIIT Pune. Welcome to our channel Learn Competitive Programming with CodeChef. If you are interested in competitive programming and want to learn data structures and algorithms, this is the one-stop destination for you. We post weekly problem explanations and concept videos. So don't forget to subscribe to our channel by hitting that subscribe button and also the bell icon. The problem that we are going to discuss today is the in-XOR-able task. The problem appeared in October Cook Off and has a difficulty level of medium. The prerequisites for this problem are dynamic programming. Our agenda for today's video is going to be as follows. First, we will walk through the problem statement and try to understand what the problem is trying to say. Then, we will see the step-by-step detailed approach to the solution, followed by which we will be seeing the pseudo code and then quickly going through the C++ implementation of the same. The problem statement goes as follows. We are given three integers n, k and x and we want to find if it is possible to find a sequence of n integers, that is a1, a2 up to an, such that the number of pairs having their XOR equal to x is exactly k. So as you can see here, if ai XOR aj is equals to x, then this counts as one pair, right? So we want to find a sequence of n integers such that the number of such pairs in the sequence should exactly be equal to k. And remember, uh, we have to output only yes or no. That is, if we are able to find such a sequence, we should output yes. If it is impossible to find such a sequence, we should output no. So we don't have to actually output the actual sequence, but we have to just give the answer as yes or no. One more important point to note down here is that there is no bound on the values that you can use in the sequence. So the values can be anything. So given a particular x, you can always find a pair such that its XOR is equals to x. But the question is it possible to find a sequence of n integers such that the number of pairs are exactly k? Let's see how to approach the solution. At this point of time, I would like to mention that if you haven't yet tried the question, give it a try and then come back to the video and continue with the editorial. Before we begin with the main solution, an important observation to make in this question is that if by some way we have a sequence of length L, that is having L elements, such that it satisfies the constraints or the conditions given in the question, that is it has exactly k pairs having XOR equal to x. So it is known that this sequence satisfies this condition. So if we know that this sequence satisfies this condition, we can always find a sequence of length greater than L satisfying the same condition. How? We can just append some elements, let's say an element small x over here, according to our need, to make the length of the sequence greater such that it does not affect this property. Why? Because there is no bound on the elements. So we can choose this x to be, let's say, a very large number, let's say infinity, so that whenever x XORed with the previous elements, it will not give the XOR as capital X. So if we have a sequence of length L, we can always generate a sequence of length, let's say L dash, such that L dash is greater than L by appending some elements at the end of the sequence. So our basic target to solve this problem is going to be as follows. Remember that for each test case, we will be given three integers, namely n, k and x. So we are going to try and find the minimum length sequence such that it contains exactly k pairs whose XOR is x, and let's say that minimum length comes out to be L, and now we know that the minimum length is L. So if L is less than or equals to n, then we can generate the sequence by appending some big numbers like infinity to the smaller sequence, or else the answer will be no. So this is going to be our basic target while approaching the solution to this problem. Now that we have made some observations, let's start to proceed towards our solution. So, as we know that there are no constraints on the values that we can choose in the sequence, there will definitely exist two integer, let's say a and b, such that their XOR is equals to x, right? And if we want k pairs in our sequence, what I can do is I can keep the frequency of a as, let's say, x1 and frequency of b as y1, wherein x1 into y1 is equals to k, because uh, how will this sequence look like? The sequence will look something like this: a will occur x1 number of times and then b will occur y1 number of times. But what will be the total number of pairs having XOR x? A XOR A will be 0, B XOR B will be 0. The only XOR remains is A XOR B, and that we know equals to x. So the total number of pairs will be number of A's into number of B's, that is x1 into y1. And if this number is equals to k, then our condition given in the question is satisfied. But now the point to observe is, what is the length of this sequence? We were able to complete the condition on number of pairs, but what is the length? The length is nothing but x1 plus y1. This is when we are choosing only one pair to get our XOR as x. But there can be other pairs as well, right? There can be some other pair, let's say a prime XOR b prime, which is again x. There can be another pair a double prime XOR b double prime, whose XOR is x. So there can be many pairs, right? So ideally, we should be targeting for a solution in which multiple such pairs are possible. But if the question was simple enough that, let's say, the sequence should contain only two distinct elements, so we could have made a sequence something similar to this. And that is how we are going to start our solution, by generating the minimum length, considering that if only two distinct elements or only one pair generating the XOR x was allowed, then what would have been the answer? So let's see how to calculate that. So if the question was simple enough such that only one kind of pair giving us the XOR as x is allowed in the resultant sequence, then we just have to find for a given k that there can be many ways to represent k, such as x into y. But what is the thing that we have to minimize? We have to minimize the length, that is x plus y. Because if we know the minimum length, then we know that any length greater than that length can yield us a sequence. So for any given k, if k can be represented as x into y, then the length is x plus y. And if you want to minimize this, this thing can be done using sieve of Eratosthenes in the following manner. So we can formulate our dynamic programming solution in the following way. So here you can see that dp of j is minimum of dp of j comma x plus y, wherein x into y is j. So what we can do is, for each number from 1 to n, let's say we have numbers 1, 2, 3, 4, 5 and so on. So for each number, for all of its multiples, we know that this number is, let's say, j, and this number is, let's say, I. So we know that j is a multiple of I. So x here corresponds to I and y here corresponds to j by I, so that their multiplication is j, and we know that j is a multiple of I, and at the same time we are minimizing the value by always storing the minimum, right? So using sieve we can easily store the answer, but only if the question was that only one kind of pair is allowed in the sequence. So the code for sieve would look something like this. So here we have our array dp of j, which is currently just storing the answer if only one kind of pairs were allowed. So initially all the dp of i's are initialized to I plus 1, and now if we have these two for loops, it ensures that it has calculated the minimum in the following way, like all the multiples of I in the array have the answer stored as minimum of dp of j comma I plus j by I. That is, if j is a multiple of I, and we know that these two quantities when multiplied give the product j, but at the same time we are also storing the minimum, so our previous discussion is applied through this snippet of code. So if there are multiple options for creating the XOR as X, our DP formulation would change. That is, earlier it was something like DP of K was minimum of X plus Y, where X into Y used to be K. But now as there are multiple options, we know that there can be multiple options, like for example, if there is A XOR B equals to X, and also A prime XOR B prime equals to X, and A double prime XOR B double prime equals to X, and let's say the frequency of this is x1, y1, x2, y2, x3, y3. So if you want to create a sequence according to the question, the summation of these things, of these products, the summation of these products should be equal to k, which is what I've mentioned here, right? So the summation of xi into yi should be equal to k, and if this thing is valid, we want such a sequence wherein x1 plus y1, x2 plus y2, and so on, xi plus yi is minimum. So this is how our DP formulation would now look like. So earlier it was for just one option, wherein only one pair was able to create the XOR X, but now as multiple pairs are able to create the XOR X, our DP formulation has changed. So how do we change our dynamic programming solution to accommodate this change as well? Let's see. So one way to include all such pairs is to again apply a DP solution. So we know that now we want to represent K as sum of one or multiple terms, that is x1 y1 plus x2 y2 and so on, such that x1 plus y1, x2 plus y2 and x3 plus y3 summation of all these is minimized. So what we can do is, we already have the answer for one pair, single pair, right? Using sieve, we have already calculated that if only one kind of pair was allowed, we have the minimum answer in the sieve. So we can make use of that DP array again in this fashion. Like for example, dp of I equals to minimum of dp of I comma dp of j plus dp of I minus j. So what we are doing here, we are breaking our current number I in two terms, that is j and I minus j. And if by breaking our I into two terms, if the answer is minimizing, then we are updating our dp of I. And similarly, as we are doing this in a bottom-up fashion, it will ensure that at all steps our dp of k or dp of I is always the minimum. But if you have observed, this is a n-square solution, right? The constraints for n in the question go up to 3 into 10 to the power 5. So n square means that the complexity would be around 10 to the power 10 computations, which is too high. So again, this solution would also not work. So we have to do some kind of optimization so that we improve our solution and fit it in the given constraints. So for optimization, let's get back to the basics. So earlier we had seen that if you want to represent k as using just one kind of pair, that is, let's say k is equals to x1 y1. So what can be the most ideal case? The most ideal case to minimize x1 plus y1 can be as follows: x is root k and also y1 is also root k. So if this happens, what will be the minimum length? The minimum length would be 2 root k, right? And if we are trying to increase the number of terms, that is x2 y2 plus x3 y3 and so on, it means that we are introducing these terms so that we can reduce the minimum length. So we know that by using just one term, the maximum length was 2 root k, right? So we can say that at any state, whatever be the number of terms, the length of the resultant sequence is going to be at most 2 root k. So this is our observation. So just now we saw that for any given k, the maximum length can be 2 root k, right? And also, if we try to represent k as sum of multiple terms, that is x1, y1, x2, y2, and so on, we are now trying to find a bound on the number of terms. Okay, so notice that x1 and y1 are the frequencies of the terms that are yielding the XOR x. So the frequency cannot be 0, right? It has to be minimum 1. So if we take the minimal frequencies, that is 1, 1, 1, and so on, so each term will contribute to the length 2, right? Because 1 plus 1 is 2, right? So in this way, we know that each term contributes 2. So, and we also know that the length can be at most 2 root k. So we can comment, so the number of pairs can be at most root k. Why? Because each pair adds up 2 to the length, and we know that the length can be maximum 2 root k, right? So this yields us the following observation. So now we know that the maximum number of terms can be at most root k, right? And they contribute at least 2, 2 to the length of the sequence. Now we are going to make another important observation. There are root k many terms, and if each of them is contributing more than root k, it means that the sum is greater than k, which is clearly wrong. So if we want the sum to remain k, at least one of them, at least one of the terms, at least one of the products is going to be less than or equals to root k. Not all of them can be greater than root k, because if all of them are greater than root k, then the sum itself exceeds k, right? So this is our final conclusion and final observation that is going to optimize our n square dp solution to even further down. So in our earlier code, it was a n square code wherein I was iterating from 1 to n and j was iterating from 1 to I. But with the observation that we have just made, we know that there is going to be at least one xi yi term that is going to be less than under root k. So it is sufficient to iterate the inner for loop not till I but just up to under root of I to get our optimal solution. Why? Because again, k can be represented as sum of many terms and at least one of them is less than or equals to root k. So that term will definitely be included if we are iterating j from 1 to root I, and that ensures that our dp of I is always optimal and minimum. So what does it bring our complexity down to? Earlier the complexity was n square, but now the complexity has reduced to n root n, and now we can see that it can easily fit in the given constraints. So if we pre-compute the answers for all possible n, that is from n is equals to 1 to 3 into 10 to the power 5, it will take the complexity n root n, and after that we know the answer for each dp of I. So for all the test cases, we just have to check if dp of I is less than or equals to the given n. If this thing happens, then the answer is yes, because if we can form a sequence of length dp of I, then definitely we can form a sequence of greater length by appending elements, right? Or else the answer would be no. I hope you guys have understood my solution. If you want to master competitive programming while learning from world-class programmers, which include ICPC World Finalists, IOI medalists, and some top-rated programmers from the world, make sure to get our subscription on Unacademy Plus. We have live classes, recorded sessions, practice problems, as well as doubt clearance on Unacademy. Also, don't forget to use my referral code DarshanKool25 for instant 10% discount. So the pseudocode for the problem goes as follows. First, we will do the pre-computation part in O of n root n. That is, using sieve, first we will calculate the minimum considering that only one kind of pair is allowed to give the XOR as X. Then, as stated in the solution, using the optimization, we calculate the dp of I so that it accommodates more than one pairs which give us the XOR as X, and at the same time their summation is also minimum. So that is handled by this uh, code. And then for each test case, we take the input that is n, k and x, and we just check if dp of k is less than or equals to n. If yes, then we can create a sequence. So we output the string yes, or else we output the string no. Following is the C++ implementation of the code. So as discussed in the pseudocode, first we create a DP array of maximum size, that is 3 into 10 to the power 5, and then we initialize it with I plus 1 because that is anyways the maximum answer possible, and then we have to find the minimum length for the sequences. So first we apply sieve to calculate the minimum in the following way, that is I goes from 1 to n and j contains the values of multiples of I, and dp of j stores the minimum, right? So once we have calculated this, as discussed in the solution, we apply the optimization, that is for I from 1 to n and j ranging from 1 to square root of I, we calculate the dp of I in such a way that multiple pairs leading to the XOR X are also accommodated in our answer, and at the same time their summation is kept as minimum. So once this thing is done, our pre-computation is complete. So now for each test case, we take the input, that is n, k and x, and if dp of k is less than equals to n, it means that we can create a sequence of length n by appending some or more uh, big terms like infinity and create a sequence wherein the pairs are exactly k. But if not, the answer is no. So we accordingly print these strings, and that's it. That completes our solution. So let's submit this code on CodeChef ID and let's hope to get a quick AC. Great, so our solution works.